So, hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar on turbomachinery optimization workflow by CAESES and TCFD. In today's webinar, we would like to show you an easy way how to optimize an axial fan created in CAESES and simulate it in TCFD. The webinar is being recorded and its recording will be made available on our YouTube channel. I hope all the techniques work just fine, and in case of any technical problems, feel free to contact us and we will gladly answer your questions and comments. Right at the beginning, I would like to stress out that CAESES and TCFD are independent software products. CAESES is a flexible parametric CAD platform produced by German company Friendship Systems. And TCFD is an unlimited CFD code produced by Czech company CFD Support. Both tools work very well together, and that's why we are here today, and we would like to show you how they work. So please let me start with introducing ourselves. So these are speakers of today's webinar. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support, and my current position at CFD Support is telling the world what we do. And I'm going to guide you through today's webinar. I am here in our Prague office with my colleague Radek Máca. Hello, Radek.
Hello, Luboš, and hello everybody who is watching us.
Okay, so Radek, are you ready for the webinar?
Yes, I am ready, as I never be.
Okay, very well. And I only note that Radek is our head engineer and senior developer here at CFD Support, and he's also a very smart person, and he's fresh father now, so he's always very hot to work, and he's like his work. Okay, so finally, together with us on the line, there is Mattia Brenner from Friendship Systems in Potsdam. Hello, Mattia.
Hello, Luboš, and hello also to all the attendees. Thanks for joining us today.
Okay, so the same question, Mattia, are you ready for the webinar?
Yes, very much so.
Okay, that's perfect. So I will know that Mattia is head of sales for Europe at Friendship Systems and also CAESES consultant and expert. So I think we are good in a good mood to provide you all the info in today's webinar. So I think we can move ahead. Here is the agenda of today's webinar. The webinar is going to take about 1 hour. There will be the following parts. In the first part, there will be a brief introduction to CAESES given by Mattia. Then I will give a little introduction to TCFD. After that, Radek will show you the joint workflow of CAESES and TCFD on the axial fan example. So it's a little study we made recently. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions to the special window below. All the questions will be answered. Some of them will be answered right away during the webinar. The rest will be answered via email later after the webinar. This is quite important part, so feel free to put your questions. It's your time. Just get involved. Take the opportunity to ask, and we are here for you, and we will gladly answer all your questions. So that's for the agenda. So I think we can move. And here I would like to pass the presentation to Mattia. So Mattia, are you ready for your part?
Yes, I am.
Okay, so here you go.
All right. Thank you, Luboš. As Luboš said, I would like to give a short introduction about CAESES. So what is it and what do we do here? As you can read here, first of all, CAESES is a specialized CAD platform that is intended specifically for running automated design studies in the connection with CFD. And before we look at the details a little bit more, let me start with some questions. So I said we want to automate our design studies. So why should I automate my design process? First of all, laws and regulations, but also the competition on the market with other manufacturers demand, as you probably all know very well, a very high level of performance in the design of turbomachinery nowadays. And the, let's say, older processes where you run through a manual iterative process, going from a CAD model, meshing it, running CFD, post-processing the CFD results. That kind of process is, first of all, time consuming, which increases the cost of development and also the development times, of course, the cycle times of the development. And this kind of process can surely lead to an improved design if you're running through a couple of design variants and comparing them to each other, but not necessarily to an optimized result, which can lead to a failure to meeting your design targets. So what automation can do for you, and I think this is not a very disputed topic, I think all of you are very well aware of that, is that automation can shorten the development times, reduce your design cycles, lead to better and optimized designs. And maybe a less known fact is that it can also help you to increase very rapidly the knowledge about your product very early in the design process, because you can run large design studies where you can analyze the influence of all your design parameters, geometry parameters, but also operating parameters, and so that you can make very well-based decisions in the design process. And to come back to CAESES, one intention of CAESES is to give you control over this process from within one user interface. Another thing that you saw in the title of my slides here is CAESES is a CAD system. So most companies are operating like some kind of CAD system in their design process. So why, the question might be, why do you need another CAD system additionally to that? And from our experience, we've been working in optimization for a long time with many customers. The typical bottlenecks in setting up and running the design optimization process or design exploration process are actually related to how the geometry is handled. And let's say typical bottlenecks that people encounter are with a traditional CAD system, geometry variation might be difficult. So you can build all kinds of geometries, but when you start to vary them in an automated way, it's tedious, or there is a very high failure rate that the geometry cannot be regenerated. That's probably the major bottleneck. Another thing that is important when you optimize a product are constraints. So manufacturing constraints or packaging or whatever you might encounter. And these kind of constraints are often difficult to consider when changing the geometry in an automated way. The third point is related to how the work is divided within a company. So often there is a CAD department that generates the geometry models, and there is a simulation department, and the simulation department is dependent from the CAD department to get the geometry model, but also to do any changes that they would like to analyze, which of course takes time, and also, as you can imagine, is not very well suited to be automated. And finally, we have a point that's related to the quality of the CAD model. So when you bring a CAD model into the simulation and you want to generate a mesh, for example, CFD mesh for this model, the quality is not necessarily suitable. So the geometry is maybe not watertight, or you have too much detail in the geometry that you don't necessarily want to consider in your simulation, and so on. And these are, let's say, typical points that we're trying to address with our specialized CAD system. So it's not a general purpose CAD system like your CATIA or Creo or something like that, but it's a very specialized system intended specifically for running optimization and design exploration processes. So let's take a look in a bit slightly more depth into CAESES. So what is CAESES? What is included in CAESES? I mentioned this already. The major part of CAESES is the internal CAD system. So here we focus on creating smart geometry models that are suitable for this kind of variation processes. We want to build a geometry with an efficient parameterization, which means we want a very flexible model that can be changed very freely, but not using too many parameters, because the more parameters we have, the longer our optimization will take. We want the geometry to be ready for simulation so that it can be transferred directly from CAD to simulation without any manual or human interaction. And of course, we want it to be robust so that if we change parameters in an automated way, the geometry doesn't break down or doesn't fail to regenerate. That's the major component. And then we have the other things that we need to run an optimization. The first one is automation. So we want to connect to a simulation tool. We're talking about TCFD in today's webinar. And we want to be able to automate the process with this simulation tool, which means we need to transfer all the input data that is needed to that tool. We need to start the process, and we need to collect the results and analyze or post-process the results. That is the automation part. And finally, we need the tools that allow us to run the actual optimization process. So the algorithms that are needed for that, or algorithms and advanced optimization strategies that we want to run. We need data management because a large amount of data is generated, and post-processing tools that allow us to analyze all this data that we're generating during the optimization. And these three things are what is included in CAESES. So finally, how can I make use of CAESES? Here we see some typical applications that are maybe not the focus of today's webinar. Maritime applications, this is where we originally come from. Ship hull optimization, propellers, things like that. Or powertrain components, so components inside of an engine, industrial machinery like valves and things like that. And then, which the focus of today is turbomachinery applications. So here we have a lot of different things that can be done with CAESES. For example, impellers. We see here some turbocharger impellers, turbine, compressor side, or gas and steam turbines are, of course, a typical turbomachinery application. Propellers, I mentioned that in the maritime already. Fans that we will look at today, but also non-rotating geometries. So most of these things we saw before, we want to optimize the blade shape of the what is rotating. And we also have other components in turbomachinery that are very important, like volutes, as you can see here, or exit casing for a gas or a steam turbine. As well as if we combine these things together, a complete system like this hydro turbine that you see here, where we have a volute, impeller, stator blades, and so on, or complete pumps. And just, yeah, that's it to give you an idea of possible turbomachinery applications. And just to conclude my part, just very briefly, who are we? Because maybe you haven't heard about us. Here at Friendship Systems, we produce the software CAESES, but we also provide all kinds of services that are related to this software, and trying to solve all the problems that our customer encounter in setting up an optimization process or running an optimization or simulation-driven design process, as I call it here. And we have been working on these things for about 15 years now. And I think this was mentioned before. We're located in Germany, in the city of Potsdam. And that's it from my side as a brief introduction. I hope this gives you a good idea of what CAESES is about. We will see later on how it is used in a specific example. And now I would like to go back, give back to Lubos, who will tell something about TCFD.
Okay, thank you, Mattia, for the CAESES introduction. So I will take back the presentation and we will move a little bit in the webinar. So now it's time to say a little bit about TCFD. So I have 3 slides for you. I'm not going to torture you too much. I'm sorry, I don't say that Mattia did, but yeah, let's go. So TCFD is a unique software developed by Czech company CFD Support, located in Prague. TCFD is smart, easy to use, and affordable CFD software. TCFD numerical solver is based on OpenFOAM, and for this reason, TCFD merges benefits of an open source, which means it's perpetual, it's unlimited in the user's jobs or cores, it's very flexible and customizable, and it also merged the benefits of the commercial codes, it has very good graphical interface, it has professional technical support, it's stable, it's well tested, robust, accurate, automated, and it's ready for the industry. So on top of that, we believe TCFD is unique, at least for 4 reasons. So number 1 would be TCFD is unlimited, which means TCFD is perpetual and users can use it for unlimited number of users, jobs, or cores. This means that TCFD can be used with our clients in a very extensive way, and it can really scale their TCFD simulations and can be used in a really big way. Number 2 would be TCFD is fully automated and focused, which means the workflow can be run by a single click or by a single command, and all the process is being done automatically. And for this reason, TCFD is extremely effective. Number 3 would be we deliver extensive technical support, which we are proud of. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in it, and our technical support is unlimited. We support our clients even in matters out of the turbomachinery field, for example, in the numerical mathematics, physics, CFD, IT, or even software engineering. The last one would be the real tutorials are included in TCFD, so the user has no doubts about the best practice settings. Basically, there is very smooth start of using turbomachinery CFD in the beginning, which is very important for everybody who wants to work with it. There are many other benefits of using TCFD. I'm not going to go for all of them. I finish here with my last point, which is that TCFD is developed in a way to support the added value of or added value activities of its users. It means that the designer should design and not to deal with boundary conditions or, for example, boundary layer or something. So the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. And at the same time, all the options are open. So it's both big, sophisticated, high-level CFD code, or it's can be used as a black box where you put the data in and just pick the data in the end of the process. Okay, so that's TCFD. I have 2 more slides with benchmarks because I have 2 little benchmarks for you to show because we put lots of emphasis to accuracy. So this one is on accuracy. So it's a benchmark which we simulated in collaboration with Czech FunMaker ZVVZ Machinery. This particular project was aimed at comparison of standard OpenFOAM and TCFD with a real measurement of a real existing fan. The case was the radial fan with very complicated airflow. It has a wide impeller and very low pressure is produced and at very high flow rate. Such a case is pretty difficult to simulate. And as you can see, the agreement of TCFD results and the measurement data are very good. Also, the steady state and transient TCFD results show very, very good agreement. So this is one benchmark I would like to show you. And the second one is aimed on TCFD parallel scaling. I only note that parallel scaling means the more cores are used in the simulation, the speed of the simulation increases, right? And parallel scaling is of our highest interest to ensure the benefit of the unlimited number of cores of TCFD will be used to the fullest. So we made a detailed study on parallel scaling of TCFD, and here you can see the results of it. Again, we can see the linear function of cores and parallel speed up, as well as the efficiency. So we can see the numbers are very good and very high. And maybe I will finish here with these two studies are also in the paper, so you can contact us and we will gladly provide you the detailed information. What's the hardware, what were the conditions, etc. Okay, so that's for TCFD introduction, and now I would like to hand over the presentation to Radek. And yeah, so Radek, are you ready for your part of the job?
Yes, I am. So please just give me your presentation. Okay, show my screen.
Here you go.
Okay, perfect. So thank you, Luboš. Hello again. So today I'm going to briefly introduce you a workflow for turbo machinery design optimization using CAESES and TCFD. So the general information about both software packages were already told, so I will be speaking just about the workflow itself and show you the workflow principles and what have to be done to really get a nice optimization with remarkable results. Well, for this purpose, we have prepared a case study for a particular design. So for the axial fan geometry, and we have created a short paper as a joint work with the friendship system, and particularly with Seyhan Erdem, who is the project and support engineer at friendship system. And the Seyhan helps me to create the parametrical design, and to basically he learned me how to work with cases, how to connect our TCFD package, and so on. So I will be speaking, let's say, from the user point of view of the cases and how it can be how the TCFD can be easily incorporated into the cases. So this is general information. And of course, for your information, this PDF we can send you after the webinar. So if you are interested in, just send us an email and we will provide you this paper. So what is today's the case study? It is the axial fan geometry, the type of a duct axial fan. So for the ventilation in piping, let's say, somehow it is referred to as the inline duct fan designed for a low pressure ventilation. So we took this geometry with the basic parameters such as the diameter, external diameter of the wheel, of course the revolutions, the maximum power, maximum pressure, let's say, maximum air capacity, and the peak efficiency for the best efficiency point. And what is, let's say, common task of the engineers in the or manufacturers in industry is, for example, both to increase the efficiency of the fan or to improve the parameters to make a new design which is more suitable for different flow rate condition. So we decided, so our task is the maximizing the fan efficiency in the new range of flow rates. Sorry, I skip here. In the new range of flow rates. Yeah, so the original maximum air capacity was 11 cubic meter per hour, and we would like to increase the efficiency in the wider range of the flow rates. So this will be our goal. So what is the workflow to just to repeat what Mattia already said? So what we need? So first we need a CAD geometry with a simulation ready export for the CFD purposes. Then what we need is to set up the CFD simulation. So usually you need to have the input geometry and some CFD setup prepared. Then you need some connector, some software connector, or some connector which connects you the CAD geometry with the CFD code, put or take the results back, and for example the results are then put to optimization tool which evaluates the results, using which it decides how to redesign your parameterized geometry, recreate the geometry, put again into the software connector, run the TCFD simulation, and so on and so on. So this is the workflow we need to set up with CAESES and TCFD. So first task is to create the geometry for the axial fan, and create the parameterization to follow both CFD purposes and ready to run export, let's say. So we do not want to simulate the full wheel just to save the computational time. So usually this axial symmetric geometries can be split into just one blade segment. So this is the rotor part, this is the stator part, and this type of geometry we need to create inside the CAESES CAD environment. Okay, then we chose 6 parameters to be designed. So I will be speaking about this particularly inside the CAESES software. So now I switch to the CAESES into the CAD part. So here we have already created geometry for the CFD purposes. So the rotor part, the stator part. Well, the CAD here, let's say it is ready to create such nice geometry with all needs for the CFD codes. For example, the beauty of the CAD here is that how to say, let's say that everything is based on the dependency modeling approach. So basically you start, everything is connected, and when you change one parameter, the other parameters are changed as well, or the geometry will never break up. So I just want to show you some nice images so I can just visualize the rotor part, let's say. Yeah, here are the parameters preset. So there are 6 parameters to be optimized. The first one is the angle of incidence of the blade. The second one is the camber parameter. So I hope it is clear. So is this camber parameter. Then the camber position of this is the third parameter. Then we have the chort length, so the length, basic length of the blade of the chort line. Then the maximum thickness. And the last but not least, there is the pitch angle at the shroud position. So these are these 6 parameters. What we kept is the number of rotors and stators, because we want to keep the initial geometry, and we do not touch the stator part just for the quicker optimization. CAESES uses a nice feature or its own feature which is called meta surfaces, which allows us to really create almost any type of surfaces we can imagine. So I can just visualize that basically it is type of extrusion of any curve, roughly speaking, and you can really preset the, let's say in this case, a radial distribution of any parameter. For example, this is the pitch angle, so you can see that I can really prescribe the pitch angle along the radial coordinate of the blade, as well as, for example, for the maximum thickness. So I can say in which part the blade will be thicker or not. So this is a nice, really nice feature of these meta surfaces. So in this case, you can model and create the CAD software, the CAD geometry for almost any shape, and then everything is prepared for the export. So this export, I can easily export it just for my CFD setup. Here, just export. There are many export types. So for us, we need this OpenFOAM STL output, so we can save it, and then there is a time for a CFD setup. So this was the parameterization. Then the CFD setup, so it's a basic CFD setup using which we can set what type of simulation, which if you would like to simulate in incompressible or compressible mode, simulation settings, so rotation speed, how many points we would like to simulate, so how many different conditions we would like to simulate. So we've chosen 6 points covering the range of flow rates in covering the all range of flow rates from, let's say, 570 cubic meter per hour up to, let's say, 1300 cubic meter per hour. We set the computational mesh, and we also, the TCFD provides an automatic post-processing such as blade-to-blade views, meridional average, variable dimensions, efficiency probes. So there are many customization we can set. So particularly, so if I go for this template TCFD, so at the beginning, what we need is just to have stator and the rotor part. So if I click, for example, on the rotor part, so this is the export ready for the CFD setup. We have the domain is split, the boundary is split into physical domains, inlet, outlets, periodical parts, hub, shrouds, and blades. So ready for the TCFD. So then here I just click on this TCFD source inside the ParaView, because you have implemented the graphical user interface directly inside the ParaView, which is a great tool for the CFD data visualization, not only for CFD. And then there is a classical setup. So here we set the machine type, simulation, how many cores we want to use. For example, my computer now has 12, but there is no limitation. Physics, inlet condition, and other. But I think this is not the purpose of this webinar. So I will load my preset case. So at the end, you will set your CFD simulation with respect to your geometry. Then you simply can run the simulation by clicking here of the TCFD manager, and I can just save the simulation into the, let's say, webinar case, write the case, and run the simulation. So when my CFD simulation is prepared, then I can go back to CAESES and connect my simulation with all the necessary stuff to the CAESES. So now I will go for the next step, which is the connection. Yes, okay, this is the optimization. So I would like to show you the connection in CAESES. So by clicking on the connection part. So now we are at the connection environment, and here we need to define just a few things. So the input geometry for the TCFD, which is just the stator and rotor part. So it is nicely, the graphical user interface is really friendly. So this is my export object. So I can click and drop and have the input data here. Yeah, so which is basically this way I have prepared this part. So I have the rotor part and stator part. Then in the TCFD, yeah, now my simulation is running, as you can see. Here in my settings, I can click save and save the configuration file here. So I can import this configuration file directly here, where the whole simulation setup is set. And then I can connect, for example, some important parameters. So what is my export? And other parameters which I can manage directly from the CAESES graphical user interface. For example, number of processors, or I can, for example, if I want to change somehow the angular velocity, I can just click, and now I have new parameter to be directly modeled from CAESES. So it is really nice and easy to use. What are the next steps? Is the result values. This is my, okay, you can add any other scripting. This is just for some report purposes, because TCFD generates automatically full report. So I just created the Python script to zip hold the report to just have the report zipped and save some storage. Then we have to define the result values. So TCFD automatically during the run. Okay, so maybe my simulation is almost ready. Yeah, it is done. So when I go to the webinar case, to the post-processing here in the efficiency, there is a nice CSV file with the results. So from this file, I can take whatever I want. Basically, using these values, I want to define the objective function for the optimization purposes. So this is done here. So I just import. I will just import my efficiency final CSV file, and then I import what I want. So we have 6 points to be simulated with different flow rates. So I just take all the efficiency here in my file, and to have a robust objective function, I also take the total pressure difference just to know if the point is in the working range of the actual design, or if it is out of the range of the design to be simulated. Okay, and the last part is to define some result files, but in this case I do not need any visualize or result files of images and other visualization, which you can prepare both in CAESES or in TCFD. And the last part is the runner, so which executable to use. So here I just said I found the CFD processor, which is the process which runs whole the workflow behind the graphical user interface, and just composer arguments which tells just what is the configuration file, and that I want to run the full CFD simulation together with the post-processing, and in which directory the simulation is stored. So whenever this is set up, we can go for the optimization and set up the particular optimization process. So there are many options which CAESES provides. So if we go here in the optimization parts, so there are many state-of-the-art optimization tools for global or local optimization, for single objective or multi-objective optimization. In addition, there is a Dakota interface, which is a big package for the optimization purposes. So there are many tools for the optimization. So we have chosen 2 of them. We have chosen one global optimization, DOE-like optimization with the Sobol sequence. So here we can set how many variants we want to simulate. In this case, 250. What are the designed variables, which are taken from the cat part, of course, the range of these parameters, and what is our objective function. Okay, so I missed to define the objective function, so I will just go back to the cat part, and here I have prepared the objective function, which is just sum of all efficiencies for each point, and the negative value because the objective function always or the optimization process minimizes the objective function. So our objective function is just sum of all efficiencies. And for example, the efficiency is defined as the efficiency, but if the efficiency has nonsense value, it means if the fun geometry or the CFD simulation gives the total pressure difference, which is lower than 0, it means it is a condition out of the working range, then it basically set the efficiency to 0, just to have the robust objective function. Okay, and back to the optimization. So here we just set which is the optimization function, objective function, and other parameters to be evaluated within the simulation. So then we can run the optimization process, and the CAESES has nice features for the evaluation. So at the end, you will give a nice table of all the designs you have simulated with the parameters, with the particular values of the parameters, with the efficiencies and the objective functions. So at the end, we took the best, okay, here in the Sobol part, we took the best efficiency point, so the optimized geometry using this global optimization, and from this we start a local optimization process using the T-search method. So this we defined here. So we just take the best efficiency point from which we start to look for the better solution just in the neighborhood of this best optimization design from the Sobol. And at the end, of course, we get the best design for this T-search. CAESES, in addition, it provides a nice tools for the, let's say, data analysis, for the dependency study. So for example, here you can see which parameter influences the objective function, how the space of design parameters is covered, and so on and so on. And last but not least, there is a nice design view using which you can nicely compare all the designs which you have simulated with the automatical, for example, plots which TCFD generates. So we can compare, I don't know, for example, flow rates versus efficiency graph for each design, and so on and so on. So you have many tools how to post-process and evaluate your optimization process. Okay, so for example, what we get, so the original geometry has this objective function around 2.4, and our best design goes up to 4. So we can say that each point, in an average, its efficiency was improved about 25%. Okay, it is quite surprising. But when we see the comparison graphs, which comes from TCFD, we can see that the new range of flow rates in which we would like to optimize the old design is out of the working range of the original design. So therefore there is such a big difference, and we can see that our new design has quite nice flat efficiency graph. Our total pressure difference is rising, so at the same total pressure difference condition there is much more higher flow rates of the new design, but the price is of course in a higher power supply for the new design. Yeah, because just to conclude, if you would like to really have a comparison of the full parameters of the geometry, we should simulate a TCFD simulation using the whole range for each design to have really comparison of these design with respect to their parameters and usability. Okay, so just to conclude, we use 300 simulation, which took just 900 course hours. So at my computer, which has just 12 cores, and it's the old one, it takes less than 3 days to run the whole optimization process. And for example, as visualization at the end, we have here comparison of the original design and the optimized design. Yeah, so the workflow is very nice and easy. It can be easily set and prepared. So it is really nice tool for, and it gives you almost unlimited options how to design, how to parameterize your model, your design, your particular geometry. And TCFD gives you unlimited source because you can really use your hardware power at 100% without any additional cost, let's say in sense of the software license. Okay, so I think this is all from my side, and I will go to Luboš. So Luboš,
yes.
Okay, so please.
Yes, of course. Okay, thank you, Radek. So I'll take back the presentation. Okay, so we have seen an example of the joint workflow of CAESES and TCFD. So we can move in our webinar. So because we are very much interested in your feedback, we have a brief survey here. So we would like to ask you now. We would like to ask the audience what is of your current interest at the moment, whether it is a parametric CAD and optimization tool like CAESES, or whether it is an unlimited CFD simulation tool like TCFD, or whether it is both together, this connection. So I will run a little survey here, and on your screens in a minute should appear a poll where you can answer. So I would like to ask you, I hope you can see it now, and I would like to ask you to answer what are you interested in. It's in the webinar, it's anonymous, so don't worry about saying something wrong. So please pick your answers, and I will let the survey running for, let's say, 20 seconds more. I can see that 65% of you voted already, so I will let it run 10 more seconds, and then I will close this survey, and I think I will be able to show you the results. So I think this is it now. So I'm closing the survey. Maybe I can share the results what we have here. Can you see anything? Okay, you can see it. So what I see is in a little window there is 23% interested in A, which is CAESES, 23%, which is the same amount in TCFD, and the most of you answered that you are interested in CAESES together with TCFD, which is good news. So okay, thank you for participating in this little survey. And yeah, I think we can go ahead. Yeah, it shows me I'm sharing the results, so I should hide it here. Okay. Yeah. And we have approached almost the end. So now let's do a Q&A session. So this is the final part of today's webinar. So we would like to ask you to put your questions. We will gladly answer them. So please take your chance. We are here for you, and we will gladly answer. And don't worry, you can ask even simple questions, because as you know, there are no stupid questions. There are only stupid answers, right? So don't worry about asking about anything. And yeah, so Radek, can you see any question you would like to answer?
So here's Mattia. So now you made me a bit worried that I'm going to give a stupid answer. So, but I will still try. There is one question I see which is related to cases from Matthias. He asked if the CAD geometry of the example that we saw is created directly in cases, and if so, is it also possible to parameterize complex turbine or compressor wheels in cases with the addition like in CF Turbo? And I would like to answer that. So yes, the geometry that we saw in the example of the fan, that's modeled directly from scratch in cases. And all the parameters that were used to run the optimization were defined as CAD geometry parameters when the model was built up. And also to your second question, if it's possible to parameterize complex turbine and compressor wheels, I think I showed a couple of examples on my slide before, where I showed different applications of cases, and it's very much so possible to model these complex geometries. Maybe if I can shortly show my screen. Oh, I have a couple of pictures here. These are impeller wheels that were modeled 100% inside of cases. So actually, we see the compressor wheel here on the left, two examples of the compressor wheel, including some stator blades here. And we also see a turbine wheel on the right side. And yeah, CAESES is definitely capable of doing the complete blade modeling, especially as Radek showed before, using these radial distribution functions that describe how the profile parameters change in radial direction. So we can model the blades. We can model, of course, the meridional contours, as well as a lot of additional details like the filleting that you see here at the root of the blades. This turbine wheel is especially interesting because it also has this webbing, or I don't know, there's different names for that, to reduce the inertia, as well as some contouring on the hub, so some end wall contouring. So yeah, you can do very, very complex geometry modeling inside of cases of these rotating geometries, but also of volutes and things like that. And I think you asked about the comparison to CF Turbo. I think some things are maybe better than in CF Turbo. I think there is more flexibility in cases, and the way things are parameterized is better for the optimization. You can include more details like the filleting and the end wall contouring and things like that, as well as all the hub or the shaft that you see here in the picture. On the other side, CAESES does not include the preliminary design capabilities that the tool like CF Turbo has. So let's say a more typical workflow that some of our customers might be using is to start the design in a tool like CF Turbo or concepts NREG or whatever there is on the market to get an initial design of their impeller wheel, and then maybe move that design over to CAESES and work on the details and do fine-tuning of optimization of the geometry. So that could be a workflow where the advantages of the two tools are combined together. Okay, I'm going to switch back to Lubos.
Okay, thank you, Mattia, for this answer. So that was okay. It's this, yeah. Maybe I can answer this question. Is it possible to solve more, to show more, or solve more examples? It would be great. From Amin, yes, we are already working on other examples which are more, let's say, complicated, more detailed, and more real. For example, the Francis turbine workflow is on the way, so you can be sure that we will deliver more complex workflows to show quite soon. Yeah, Puria is asking, can you call this a kind of AI, right? We would like to, which means artificial intelligence. We would love to, but I think from my point of view, artificial intelligence is another level of virtual prototyping. But this is something on the way, I would say.
I would agree with you. I think there is still the engineer at the computer is still needed here to define the optimization task, to define the design space that we are analyzing and so on. So let's say the busy work and the boring work is left to the computer, but maybe not. We're not moving so much real intelligence over to the computer. I would say.
It's still intelligence, but it's not artificial, right?
Yes.
Okay, I see an interesting question from Sudhir. So, can we perform car park ventilation and the data center cooling analysis on TCFD? Yeah, I have to say TCFD was originally developed for rotating machinery, but in the last year we moved quite a lot in this, and we are moving to it always will be TCFD. It always will be a focused simulation workflow. So we will probably never make it general purpose code. It will always be focused, and let's say car park or data center is not implemented yet as a workflow, which means that the answer is no at the time being, at the moment. But in the future, let's say a ventilation or a room heating is one of the very hot candidates to be added to TCFD. So we can look forward to have it in TCFD quite soon, I guess.
Maybe I can take something again. I see there is two related questions from the same person. Brian asked about the method used for the design of experiment in this case here. So in this case, we used the Sobol algorithm or Sobol sequence to run the design of experiments. It's I mean, you can look up the details, but it's a low discrepancy sequence that tries to cover the design space as uniformly as possible. Yeah, I think you can see here a little bit I mean, these are, of course, we have an n-dimensional design space, and these are slices through that design space, but you can see how the points, the designs are distributed evenly with a certain kind of pattern within the design space, and that's typical for the Sobol sequence. And there is a related question, as I said, from Brian. He asked 6 parameters are involved in this optimization, and every parameter has 4 settings. It would be about 1,300 cases to simulate. That's actually not the case. I mean, we did run 6 parameters in the optimization study, but each parameter did not have 4 settings, but it has a range between a minimum lower bound and an upper bound, and then it can take any value within that range. And which value is selected for each parameter is decided by the DOE algorithm, the SOBOL, or by the optimization algorithm in the secondary step of the optimization, the T-search algorithm in this case. So that's why we're not necessarily have to run these 1,300 cases here.
Yes,
okay.
Yes.
I think someone was trying to say something. Maybe Rade?
Okay, sorry.
Yeah.
Yeah, okay. Thank you, Mattia, for explaining this. Yeah, the SOBOL sequence, as you told, try to randomly cover the variable space to have the best distribution, to have the best distributed point. So if we compare it to the uniformly distributed point, as maybe Brian proposed, that if each parameter, for one setup of parameter we have 6 different parameters, so it's 6/4, right, or something like that. So the SOBOL covers the parametric space in more clever way than to have just uniformly distributed points, I guess. Yeah. Okay.
Yep.
Okay, so I think we should move. The time is almost over, so I will finish the webinar. So I think this is it from us in the webinar. So feel free to contact us. I'm sure you know very well how to do that. The questions about cases are to be sent to Friendship Systems. The questions about TCFD are to be sent to CFD support. So we will gladly support you in your project. So feel free to contact us. We will do our best. It's our job and also a pleasure. Anything more to say, Mattia?
Yeah, maybe just from my side, feel free to visit our website on www.caeses.com, or just Google for cases and you'll find it. And also related to the question that was asked before about the modeling capabilities for impellers or other types of geometries, you can look on the website under industries, turbomachinery, for example, and there you will see a lot more information about the capabilities of the system. Yeah.
Okay, Radek, would you comment?
Okay, just I would like to thank all of you who is watching us online or offline later on. And if you have any question, if you are interested in some particular thing in TCFD in cases or in the connection, so do not hesitate to contact us. We will gladly answer you all of your question and help you with your projects and with your designs. Thank you and goodbye.
Thank you very much from my side as well. Bye-bye.
All right then. So we leave you with that. Thank you for your attention and we are looking forward to collaborating with you. Stay tuned and bye-bye for now.